So, student, today we are going to start the new topic as your kinetic theory of gases and radiation. Now, what we are going to study under this kinetic theory of gases? First, we have to concentrate on this point as a gas. What this gas is? This gas is nothing but one of the state of matter. Already from fifth standard, we are saying there are number of states of matters. Until date, the 5 states of matters are discovered. Out of that, the very familiar states of matters are nothing but your solid. Second, we are saying as a liquid. Third, we are saying as a gas, which we are going to study under this kinetic theory of gases. The fourth state is nothing but plasma. And the fifth state is nothing but the Boltzmann. So these are the 5 states of matter which are up till time is discovered. In that, the first 3 are very familiar. We are less familiar with this fourth state as a plasma and the fifth state as a Boltzmann. Right? Now, here in this chapter, we are going to concentrate on the third state of matter, which is nothing but the gas. Now, regarding this gas, in 9th standard, from 9th standard, we have seen the different laws. In that, one of the laws which we have studied, which is nothing but as your Boyle's law. What that Boyle's law? This Boyle's law says that pressure is inversely proportional to volume, provided that the temperature will remain constant. So if temperature is constant, then pressure is inversely proportional to the volume. This we have studied as a Boyle's law. Then second thing which we have studied, which is nothing but as your Charles law. Under that Charles law, we have studied that volume is directly proportional to the temperature, provided that the pressure will remain constant. So when pressure is constant, your volume of the gas is directly proportional to the temperature. And this law is going to be called as your Charles law. This we have studied. Then we have seen as the Gay law. What that we study? It says that pressure is directly proportional to the temperature, provided that the volume of gas will remain constant. So this already we have studied. This is just a revision. Which type of gas laws we have considered till date. So first, Boyle's law, which gives the relation between pressure and volume. Charles law, which gives the relation between volume of gas and temperature. And the Gay's law, which gives the relation between pressure and the temperature, provided that the volume of the gas will remain constant. Right? And means what? If you are concentrated on these 3 laws. So 3 laws gives the relation between 3 physical quantities, which is nothing but your pressure, volume and temperature. So if your pressure, volume and temperature, these are the 3 physical quantities. Along with that, we have related all these 3 laws. Right? Now, if all these 3 laws we combine together, then we can write down one more relation. And that relation is nothing but your PV upon T will always remain constant. And furthermore, we are writing that as a PV is equal to nothing but nRT, which is called as your ideal gas equation. So this ideal gas equation gives the relation between pressure, volume and temperature. Now this n is nothing but the number of moles. R is nothing but your gas constant. This gas constant value is nothing but your 8.3. This gas constant value R is nothing but 8.314 joule kilomole raised to minus 1. So joule mole raised to minus 1, Kelvin raised to minus 2. That is nothing but your gas density. Now this N is nothing but your number of moles. How you can give the definition of this number of mole? This number of mole is nothing but your capital M upon Mc or capital N upon Na. Now what is the meaning here? M is nothing but the mass of the gas. Mo is nothing but the molar mass of the gas. So the ratio of mass of the gas to the molar mass of the gas is nothing but your N. That is number. Or it is ratio of N. Capital N. Capital N is nothing but the number of molecules, gas molecules, divided by Na. Na is nothing but the Avogadro's gas number. So like that manner, this gas will be related with these three physical quantities, which is nothing but as your pressure, volume and temperature. Right? And therefore, now we are going to concentrate on very important topic, which is nothing but the pressure exerted by the gas molecule. So that if we are considering, we are enclosing gas molecules inside a container. Now which container we are going to consider? We are considering a cubical container. So I say that, let's consider here is nothing but the cubical container. This cubical container has length, breadth and height, which is nothing but L. So I can say that length is equal to breadth is equal to height, which is nothing but as a capital L. And therefore I can say that area of that surface area of that cube is nothing but L square, and volume of that cube is nothing but your L cube. And inside this cubical container, we are enclosing number of gas molecules. So I can say that inside this container, I am enclosing the number of molecules as a capital M. Now, gas molecule, we are knowing the properties of gas molecule. That is, gas molecule always moves randomly inside the container. Gas molecule has mass. Gas molecule has a volume. Gas molecule will randomly traveling inside the container. During that case, it will collide with each other as well as it will collide with the wall of container. And this every collision is to be considered as an elastic collision. Right? Then, when these gas molecules are moving inside the container, they will collide with each other. When one gas molecule will collide with the neighboring gas molecule, that collisions we are neglecting. Then which collision we are going to take under consideration? We are going to take the collision which are under considerations are nothing but when gas molecule will collide with the wall of container. So when gas molecule will collide with wall of the container, at that time, wall of the container will exert a pressure on a gas molecule. And that we want to calculate. So here we want to find out pressure exerted by the gas molecule. This I want to calculate. And for that case, what I have said that here I am enclosing this cubical container along this XY coordinate system. Right? And I am considering the collision of this gas molecule with respect to this dark shaded surface. So this dark shaded surface is marked as a S. And consider the collision with this S surface, which is shaded. Now what I'll do, I will select one of the gas molecule 1. This gas molecule 1 will be traveling with certain velocity along the x-axis, parallel to x-axis. So that's why this velocity I am going to call it as a Vx. Right? As it is traveling along x-axis, that's why I am saying the velocity component of that molecule along x-axis is nothing but Vx. I am considering a single molecule. So single molecule, that's why I am saying that for m is nothing but the mass of gas molecule. This gas molecule is traveling with velocity Vx. Vx is nothing but the x component of velocity. So now this number one molecule is moving with velocity Vx and it is traveling towards this shaded region which is marked as S. Therefore, I can say that the initial momentum of that gas molecule, Pi, I for initial, P is a momentum. So initial momentum of that gas molecule is nothing but m into Vx. With that momentum, molecule is traveling from origin to the surface area S, opposite surface area S. Now this surface area S is parallel to your XYZ plane. And hence here what we are considering? We are considering that is when molecule is traveling along x-axis, its only effective velocity component is Vx. We are neglecting its y component and z component. Because your molecule is traveling parallel to x-axis, collide with surface S, which is parallel to the yz plane. Therefore, I am saying that the initial momentum of the gas molecule Pi is nothing but m into Vx. Now, when your molecule start traveling from origin, come to surface S, it will collide on S surface. According to concept, when gas molecule will collide with the surface, the collisions are elastic. Collisions are elastic means what? There is no loss of energy. So energy will be not lost, but your molecule will rebound. So molecule changes its direction of velocity. Now it will travel towards the origin of the cubical container with negative direction, towards the negative direction. Means now when it will rebound, so after rebounding, its velocity will become minus Vx. Direction of velocity is opposite to that of your initial one. Therefore, this velocity I have taken minus. So I can say that the final momentum of that gas molecule is nothing but minus m into. Therefore, change in momentum delta P, which is nothing but final momentum minus initial momentum. Your final momentum is minus mvx, minus initial momentum is mvx. Means your change in momentum, this change in momentum will become as a minus twice m into vx. This is nothing but the change in momentum of a gas molecule. Right? Now, due to this change in momentum of a gas molecule, change in momentum is minus twice mvx. Is the change in momentum of a gas molecule. During collision, collisions are elastic. Therefore, I can say that the momentum, I can say as a momentum transfer to the wall of container that I will write down as twice m into here. It is positive. Why? Because this is the change in momentum of gas molecule. This gas molecule gives its momentum to the wall. So the momentum transferred to the wall is nothing but plus 2m into x. It will become plus. Because net momentum is 0. Because every collision is elastic. Every collision is elastic means what? Whatever amount of momentum is given to the wall, same momentum will rebound. So gas molecule gives minus twice mvx momentum to the wall. Wall will rebound. So direction will change. Minus side will become plus. So the momentum transferred to the wall of container is nothing but twice m into. Is it right? Okay, fine. Then now I can say that during that case, when your molecule will collide with the surface S surface will exert a pressure. That pressure will be exerted by surface area S. Therefore, I can say that the average force exerted is nothing but the rate of change of momentum, or I can say that this average force is nothing but, I can say as the average force F is nothing but your, according to your Newton's second law. What Newton's second law says that force is nothing but rate of change of momentum. Momentum, that's why I am saying P, which is equal to nothing but change in momentum divided by time required, which is nothing but your average force. This equation we have written from Newton's second law. Newton's second law says that rate of change of momentum imparted to the particle is always remains constant. So average force is equal to nothing but rate of change of momentum. Rate of change of momentum means change in momentum per unit time. So this change in momentum of what? Wall. Because wall will exert a force. Therefore, I can say that here your average force is nothing but twice mvx upon t. Now we have to find out value of t. T is what? Time required between two successive collisions between the molecules. So now, your molecule will start from origin. It will travel towards S. So it will travel a distance L, capital L. It will collide with S. Rebound, again come to origin. So again it will travel a distance L. Right? Means what? In two successive collisions, the molecule will travel a distance which is equal to nothing but, in successive collision, the distance traveled is nothing but 2L with velocity Vx. Therefore, from definition of Vx, I can write down Vx is equal to distance upon time. Distance is how much? Distance traveled in successive two collision is twice L divided by time required is nothing but small t. Means what I write down here, I can write down time t is nothing but twice L upon Vx. This is nothing but the time taken by the particle during the successive collision. Clear? This is nothing but, here I am getting average force from your Newton's second law. Here I am getting time from definition of velocity. Clear? Now I can put value of t in this average force formula. So if I substitute the value of this average force, t value in the average force, I can get the equations. Clear? So I can do that thing I can put the values. Force, average force is equal to twice mvx upon t, equation number 1. Instead of t, I can put value of t from equation number 2, which is nothing but twice L upon vx. 2 factor will get cancelled. Vx will go to the numerator. So I am getting mvx square upon L is nothing but your average force. Clear? So this average force will be exerted by the gas molecule. Fine? Therefore now I can find out, this is the average force. So now I can find out the average pressure. We have a formula for pressure. Pressure formula is nothing but average force upon A. The simple formula of pressure is equal to force per unit area. But here we are calculating average pressure. Therefore, average pressure is equal to average force upon area. Average force which we have mvx square upon L divided by area. Which area exerts a pressure? S. S has a length L, breadth L. So area is L square. So that L square I can put it here. So what I am getting here? Your average pressure P is equal to m Vx square divided by this L cube. And L cube is nothing but the volume of the cubical container. So m Vx square upon, that is nothing but as your average pressure. Clear? Now, once we got this average pressure, but this average pressure is of what? First molecule, only one molecule. So what I can say that this average pressure is of molecule number 1. So now if I am considering another molecule, second molecule, whose velocity is again along parallel to x-axis. That velocity I am going to call it as Vx2. So that will exert average pressure, which is nothing but m Vx2 square upon V. V is nothing but the volume. Clear? So now I can write down here. Okay, see here. Why I am calling it as a Vx1? Because this is first molecule which we have considered. I can consider there is a second molecule. So second molecule has another velocity which is parallel to x-axis, which is nothing but Vx2. Therefore, what I can say here, I will call it here as nothing but your pressure. I will say as a pressure P is equal to m divided by V. This inside the bracket. First molecule Vx1 square plus Vx2 square plus Vx3 square. Like that, number of molecules are there. That is nothing but as your pressure. Is it right? Therefore, now I can say that the average velocity of all molecules which are traveling along the x-axis, that I can write down average square of average velocity of all molecules traveling along the x-axis can be written as Vx1 square plus Vx2 square, number of molecules divided by n, because there are n. So what I will say that n Vx square average is equal to nothing but Vx1 square plus Vx2 square plus delta number of molecules. Means for this bracket field value, what I am getting, it is nothing but n average Vx square. Means now my pressure equation becomes, this pressure equation I can write down. P is equal to m upon V into bracket n Vx square. Now this V is a small v for velocity and this capital V is nothing but the volume. So just concentrate this, what is capital V? Capital V is nothing but the volume of gas molecule and small vx is nothing but the velocity of all gas molecules which are traveling parallel to the x-axis. That is nothing but the velocity. Clear? Now here I can say that, therefore I can say that now your average gas molecule here, total molecule how much I am considering? M. But all molecules are not traveling along the x-axis. Some molecule will travel along y, some molecule will travel along a z-axis. Means in short what I can say that I will write down Vx square is equal to Vy square is equal to Vz square, which is equal to 1 by 3 V bar square. Right? Means instead of this Vx square, what I am going to write down, it is nothing but M upon capital V into N into 1 by 3 Vx bar square. Sorry, V bar square. Have you got why I have taken this 1 by 3? Right? Again look at it. Total number of molecules inside the cubical containers are N. Out of that, 1 by 3 N molecules are traveling along x-axis. Therefore, this Vx square is replaced by 1 by 3 V square bar. Bar matlab average. Right? Therefore, now what I am getting here? So I am getting now this pressure. We will write down this. Pressure is equal to M upon capital V. M is the mass of gas molecule. Capital V is the total volume of gas molecule inside the bracket. N by 3 V bar square. Therefore now, instead of small m into n, small m is the mass of one gas molecule. Capital N is nothing but the total number of gas molecules. Therefore, I can write down here as, instead of this, I can write down the equation 1 by 3 N M V bar square upon capital V. That is nothing but the pressure exerted by the gas molecule. Only I have rearranged it down. 1 by 3 N. M will be taken nearer to average velocity. And this is nothing but your pressure exerted by the gas molecule. Getting? Any doubt here? Clear? Okay. Now, this V bar square that I can replace with the help of your average velocity. Now, here what I am getting? A pressure expression. I am getting here pressure P is equal to, here, pressure P is equal to 1 by 3 N, number of gas molecules, small m, mass of the molecule, V bar square, square of average velocity, capital V, volume. That I can write down. V bar square can be written as PV, 3PV, right, divided by N into. This is nothing but your square of average velocity. Get it? Now, this square of average velocity, instead of this PV, now I can substitute your ideal gas equation. What is PV? PV is equal to nRT. That is your ideal gas equation. So I can put the value of PV as an nRT. So what I am getting? V bar square is equal to nothing but 3. Instead of P, we'll say N, R, T upon capital N into small. Are you getting this? Any doubt? Now, instead of this N is nothing but the number of mole of gas. So already I have given that formula. Number of mole of gas is nothing but capital M divided by molar mass, or it is equal to total number of gas molecules divided by Avogadro's gas number. So instead of this value of N is capital N upon Na, that I can put it here. So 3 N R T upon Na into N into N. That I have substituted. Is it right? And now here this N into N instead of this. This is nothing but the total mass of the gas molecule. And that total mass of the gas molecule, that I can substitute as a, see here, this N factor will get cancelled. What I am getting here, this Na into mass, which is nothing but as a molar gas molecule, molar mass of the gas. So see here, instead of M into Np, I can substitute molar mass of the gas molecule, M4. So what your value? Velocity will become V bar square, which is equal to nothing but P R T upon M4. Right? Means I can say that V bar is equal to under root of 3RT upon M4. And this velocity is to be called as root mean square velocity, which is to be called as your RMS velocity. So this is called as a RMS velocity, or it is to be called as a root mean square velocity. Clear? So like that manner, we are getting these two formulas. One is for pressure exerted by the gas molecule, and another will be for the root mean square velocity of the gas molecule. Getting? In that, see that RMS velocity, I can say that RMS velocity is directly proportional to root of T, because R is gas constant, M0 is the molar mass of the gas, which is also constant. So your RMS velocity is dependent on the temperature. So RMS velocity is directly proportional to the root of T. So that type of question also comes in. Only for this. Show that RMS velocity of the gas molecule is directly proportional to the square root of temperature. And this is your long question, 3-mark question. Derive expression for pressure exerted by the gas molecule. Clear? So now I will give you the steps from the textbook. Which steps to be underlined for the question pressure exerted by the gas molecule. So your first question is derive expression for pressure exerted by the gas molecule. For that, see your page number 58. From 58 page, you have to draw the diagram. Diagram figure number 3.2. And now you have to describe this diagram. That is your step number 1. What is description? Consider a gas is enclosed inside the cubical container of length L. Therefore, surface area of the cube is L square. Volume of the cube is L cube, which encloses n number of molecules. Therefore, volume of gas molecule is also L cube. Second point. Inside this cubical container, your gas molecules are moving randomly. First point. Under second point, first point. Then next point. During random motion, gas molecules collide with each other as well as it will collide with the wall of container. Third point. When they will get collide with molecule to molecule, intermolecular collision, that is negligible. But when that gas molecule will collide with the wall of container, then wall of container will exert a pressure. And that pressure we want to calculate. Clear? For that purpose. Point number 3. What we are going to consider? We are going to consider a first gas molecule which is moving parallel to x-axis with velocity Vx1. Travel towards the surface S, covers a distance capital L, so that the initial momentum of that gas molecule is mx1. When that gas molecule collides with S, it will rebound with opposite direction. So velocity will become minus Vx1 and come towards the origin. Therefore, final momentum of the gas molecule is minus mvx1. Hence, change in momentum equal to final momentum minus initial. Your final momentum is minus mxvx1 minus initial momentum is mvx1. So the change in momentum of a gas molecule, that is delta P, is equal to minus 2 mvx1. During collision, gas molecule will transfer its momentum to the wall. Therefore, momentum transfer to the wall of container is opposite to that of your gas molecule. Gas molecule momentum is minus. Therefore, momentum transfer to the wall is plus, which is equal to plus twice mvx1. Right? Now, when your molecule will get rebound, your surface S will exert a certain force. Therefore, I can write down, according to Newton's second law, the average force exerted by the wall of the container is equal to rate of change of momentum. Rate of change of momentum means delta P upon T. But which delta P? Change in momentum from the wall of container, which is twice mvx. And its rate. Rate means divided by T. So your average force is equal to, see here, the average force is nothing but equal to twice mvx1 upon T. Now T is what? Time required between two successive collisions. During successive collision, molecule will travel a distance 2L. See here, from origin to S, distance L. Collide, rebound, again distance L. So total distance traveled is 2L with velocity Vx. Therefore, according to definition of velocity, velocity is equal to distance upon time. Velocity is Vx1 of first molecule. Distance traveled is 2L upon T. So time taken is 2L upon Vx. So that time interval T, I am going to put in the average force equation. To see that, your equation number 3.8 on page number 59. Average force is equal to average rate of change of momentum. Rate of change of momentum means change in momentum, which is twice mvx1 divided by time. Time is what? Twice L divided by Vx. So 2 factor will get cancelled and Vx1 factor will get multiplied. And therefore we are getting average force, which is nothing but equation 3.8. Clear? Once we got that average force of one molecule, I can concentrate on second molecule. Second molecule velocity is Vx2. Third molecule is Vx3. So if I add all that force, so what I am getting? The force exerted by all the molecules which will traveling parallel to x-axis will be nothing but, see that equation 3.8 is m by L Vx1 square plus Vx2 square like that. That is the total force exerted by all gas molecules which are traveling parallel to x-axis. Then average pressure. So pressure formula is pressure is equal to force upon area. So I write average pressure is equal to average force upon area. Average force is already given, divided by area. Area is L square. So I am getting P is equal to M into bracket Vx1 square plus Vx2 square plus dash dash divided by LQ. Clear? Now whatever your bracketed quantity, that is average of square of x component. So average of square of x component is V bar Vx square bar is equal to, see here that equation number 3.9 is given. I can write down equation number 3.9. But here I am considering the pressure exerted by the gas molecule which are traveling only along x-axis. But some molecule may travel along y, some molecule may travel along z. Therefore, if I am saying that total molecules are n, that n molecule will get distributed along three axes. Some will go to x-axis, some will go to y, some will go to z. So I'll do the equal distribution. N by 3 molecule goes to x-axis, N by 3 molecule goes to y-axis, and N by 3 molecule will go to z-axis. Therefore, I can replace your Vx, Vx square bar as 1 by 3 Vx V square bar. And then I am getting equation number 3.10. Clear? And that is nothing but your pressure exerted by the gas molecule. Fine? Now, once you got this pressure exerted by the gas molecule, now I can write down for V square bar, which is called as root mean square. This velocity is called as the root mean square velocity. I want to find out root mean square velocity. For that purpose, I can write down average of square velocity from this pressure equation in this manner. Instead of PV, I can use ideal gas equation as an example. Instead of PV and RF. Then I put value of N. N is nothing but capital N upon NA. So that I put it as a capital N upon NA. And N factor will get cancelled. Smaller into Na is nothing but the molar mass of the gas, which is density. So instead of M into Na, I will replace it as a density. And then I will get root mean square velocity is equal to under root of 3RT upon mc. R is gas constant, m0 is the molar mass of the gas. So your RMS velocity is directly proportional to the square root of. Yeah. So today I will stop here. Next time we can see the next one. Clear?